Greetings, Cantaloupe here with another video, and I'm going to be covering something interesting to me. I use it a lot in my animations, my graphical stuff. It's a type of spatial deformation. I've touched on deforming objects in past videos, or one past video. This one's going to be specifically about collisions with an elasticity kind of variable involved. It's spatial elasticity, and you'll see as I go through it kind of how it unfolds, and I'll explain what I'm doing. So let's jump in.
You got it. All right, you want to go? You got it.
When I set out to make this demo, my goal was actually not exactly what ended up happening, and I've spoken previously about how experience in programming or animation or really anything enables you to drive. It makes you more decisive, more directed as to what comes out of it. And in this case, I was very close, but I kind of decided near the end to abandon my original plan, which is allowed. It's your own project, and people aren't expecting anything out of it necessarily. You're allowed to drive in whatever direction you like and change directions, change your mind. That's fine. That's what I did. So I began with the idea I was going to make a very straightforward spherical collision demo, and then explain how that happens. So I did that part. That's actually the first part here. You can see on the screen I'm making the kind of a very large or very numerous bowling pin kind of configuration with some shapes or some little marks on the screen at this point. It's a two-dimensional triangle made up of little dots. But what's happening in the code right here is those dots each have a handful of properties. Each one has an independent set of properties, and that is position. It looks two-dimensional on the screen, but the position is actually three-dimensional, and it's each particle is a good way to describe it in terms of programming and graphics. There's a thing called particles, and it's basically a vertex or a point in some space, two-dimensional or three-dimensional space, that has some properties to it. These ones, as I was just saying, appear two-dimensional, but they're actually configured to be or become three-dimensional, and you'll see that they do that in a moment. But what's interesting is they don't just have a position. There's a bigger handful of properties, and it includes what's called a vector. If you know anything about vector math, it's a magnitude, a direction and magnitude, but not anything else. So you can have a vector and attach it to a position, or you use the vector as a kind of a delta. I'm using some math terminology here. A delta is a change in something over time. So if you are every frame or every period applying your vector to your position, which is what I'm doing, you end up with something similar to like a velocity. I'm kind of just turning this other set of variables or values into movement. So there's the three dimensions, x, y, and z. You can think of them in those terms, those letters. And I'm applying, in my mind, it's vx, vy, and vz. It's velocity x, velocity y, and velocity z, which is a single vector. You can imagine it as a single vector. And then you can do vector math with multiple vectors and get angles and all kinds of stuff, but that's beyond the scope of this video. So anyway, each particle has a position, a vector, and what I end up doing at the end is giving each particle a reference to its original position. And why I want to do that is because I'm going to combine a few things, including the movement, the collision detection, and actual reflection or bouncing of the objects off of each other, but also the elasticity I spoke about, the elastic space, which means that they're going to want to try to return to their original positions. They're going to bounce off of something. I'm adding colliders at this point. So I have a collider, and I'm making the particles respond to it when they come in contact. So they move away from it, obviously, and they bounce off of it. And then they're going to try to interpolate is the word. They're going to interpolate their position back to where they started. So you get kind of an interesting effect out of it. And I use this in a lot of graphics. I use this in a lot of demos. The particles will kind of fly out, and I've got a dampening equation in there as well that it just reduces the velocity constantly wherever the particles are, whatever they're doing. They're basically, they have kind of a drag effect. You just divide the velocity by a fixed number, 1 point something greater than 1. It's going to make it smaller every frame. So you kind of fine tune it. And a lot of what I'm doing in the program is fine tuning. I have what I like to think is sort of a high standard of quality for the output. I don't want to necessarily show anything or keep anything that isn't interesting or artistic, I guess. I don't know. So I stick with it. I don't settle for less than something great. And I think that's a trait of a lot of successful artists or programmers or just anybody, really. You get what you settle for, I like to say. But anyway, so toward the end of this sequence of changes I'm making, it's going to become what you see down in the goal. Right about here is where I decided to diverge from my original goal of having a bowling pin kind of simulation from the top down into a three-dimensional simulation. I turned it into, I extended it along the perpendicular plane to the XY plane, which is the Z plane. So I just mirrored the triangle along the Z plane. So there's basically two perpendicular triangles, and then the collider is going through them, and you see the particles are responding to the collider as you'd expect. And right now what I'm doing is I'm constantly changing the amount, the magnitude of the bounce, like when they bounce, what happens when they come in contact. You can control all of that. These are all based on the distance formulas I've discussed in past videos. How you detect the distance between two-dimensional points. You use the hypotenuse between them with a right triangle. Using the Pythagorean theorem, that extends very naturally to the third dimension and beyond. You can check the distance in the exact same way. Instead of a squared plus b squared equals c squared, you just have three components, and there's a three-dimensional hypotenuse, and it's the exact distance. So when the distance between the center of the collider, which is the bigger circle on the screen, and the particle, which also has a radius, when that distance between them is equal to or less than the sum of both of their radiuses, radii, I guess, I don't know, then they're in contact. And at that point, I have to decide, do I want them to simply be repelled, or do I want them to actually be repositioned and repelled? And I find that the most interesting effect is kind of a combination of both, but it's not always super easy to get to that point. But anyway, you see the video has finished, and I've completed the animation, and if you have any questions, feel free to reach out. I'll leave my contact information on the screen, and have a great day. Thanks.